Hi everyone. In the last video, we talked about single objective optimization and finish off with the definition of stochastic optimization algorithms. In this video, we're going to be talking about the stochastic optimization algorithms a little bit more. There are different classifications for the stochastic optimization algorithms. In the most well-regarded classification, such techniques are divided into two classes. In the class number 1, an optimization algorithm starts with one solution. This solution is then improved and evaluated until the satisfaction of an end condition. In the second class, however, a set of solutions is employed to determine the global optimum for a given optimization algorithm. In our analogy, if one person searches for the global optimum, the entire search process is individual based. If more than one person look for the treasure, however, the search process is population based. The advantage of individual based algorithm is the need for the minimum number of function evaluations. The number of function evaluations is equal to the number of iterations. However, such techniques suffer from local optimal stagnation or premature convergence. This is because a single solution is very likely to be trapped in local solutions. And if you remember, in the last video, I showed you that there is a lot of local solutions when solving real-world problems. By contrast, population-based techniques benefit from high exploration of the search space and lower probability of local optimal entrapment. If a candidate solution goes inside a local optimum, other solution will assist to avoid it in the next iteration. As drawbacks, such algorithms require more function evaluations and are computationally more expensive. There is no doubt that the advantages of population-based algorithms outweigh their drawbacks. High local optimal avoidance and exploration make population-based algorithm a better solution to real-world problems as compared to the individual-based algorithms. To solve optimization problems, both population-based and individual-based algorithms employ two conflicting and fundamental phases: exploration versus exploitation. These two phases are essential to find an accurate estimation of the global optimum for any given optimization problem. Some people call these two phases diversification versus intensification. To better understand the concepts of the exploration and exploitation, let's have a quick look at our analogy once more. In order for the badge team to find the treasure, the members need to first find the deepest valley by searching the mountainous region as extensively as possible. This corresponds to exploration in stochastic optimization algorithms. The main objective is to find the most promising area of the search landscape. After finding the promising valley, all team members should focus on finding the treasure buried somewhere at the bottom of the valley. Of course, the search does not have to be as extensive as the exploration phase, since the team has a rough idea where the treasure is. There might be small hills and valleys, but the team does not need to go from one region to the next. In other words, they can conduct the search operation locally. Local search in the desired region of the mountainous area corresponds to the exploitation in a search landscape. Population-based algorithms improve the set of initial solutions constantly to eventually estimate the global optimum. In the exploration phase, an algorithm abruptly changes the candidate solutions to ensure that they explore different regions of the search landscape. At this stage, a rough estimation of the global optimum is found. The exploration can be done with frequent or large changes in the solutions. Different types of algorithms require different operators to show exploratory or exploitative behaviors. In the exploitation phase, the magnitude of changes in the solutions is much lower than that in the exploration phase. In other words, the search is done locally around the most promising solutions found in the exploration phase. The mechanism of exploitation is again different depending on the type of an algorithm. What makes the process of designing and utilizing population-based algorithms difficult is that the exploration-exploitation phases are in conflict. A mere exploratory behavior mostly results in finding very poor solutions, since the algorithm never gets the chance to improve the accuracy of the solution. By contrast, mere exploitative behavior results in trapping a local solution because the algorithm never gets the chance to change the solution abruptly. A good balance between the exploration and exploitation leads to finding a very accurate estimation of the global optimum for all types of optimization problems. However, the challenge is that the intensity of these two conflicting phases is hard to define and balance. Finding a good balance between the exploration and exploitation is difficult and depends on the shape of the search landscape. As a solution, it is common to use adaptive operators to tune exploration and exploitation proportional to the number of iterations. This means that the algorithm smoothly transits from the exploration to the exploitation as the iteration counter increases. Another popular technique is to promote exploration at any stages of optimization if there is no improvement in the best solution obtained so far. Alright, let's talk about different classes of population-based optimization algorithms. Population-based algorithms can be divided into three classes: evolution-based, physics-based, and swarm-based methods. Evolution-based methods are inspired by the laws of natural evolution. The search process starts with a randomly generated population which is evolved over subsequent generations. The strength of these methods is that the best individuals are always combined together to form the next generations of individuals. This allows the population to be optimized over the course of generations. The most popular evolution-inspired technique is genetic algorithms that simulate the Darwinian theory of evolution. Other popular evolutionary algorithms are evolution strategy, genetic programming, and biogeography-based optimization. Physics-based methods imitate the physical rules in the universe. In this figure, you can see the name of some of the most popular algorithms in this class. The third group of nature-inspired methods includes swarm-based techniques that mimic the social behaviors of groups of animals. Popular and most well-regarded techniques in this class are particle swarm optimization and ant colony optimization. In a later video, we'll go through some of these algorithms and analyze their mechanisms. But the good thing at this stage is that you know how they all work. The frameworks of all these algorithms is almost identical. They start with a population of random solutions. With the specific operators to perform exploration and exploitation, they then estimate the global optimum for a given optimization problem. You might ask me why there is a lot of algorithm in each class. If the framework is identical, what would be the merit of each algorithm? Your answer is in one of the most well-known theorem in the field of optimization called no free lunch theorem. This theorem logically proves that there is no optimization algorithm to solve all optimization problems. According to this theorem, all algorithms perform equally when averaged across all possible optimization problems. Therefore, one algorithm can be very effective in solving one set of problems and not effective on a different set of problems. This is a foundation of many works in the literature. Before we finish off this video, it is worth discussing here that some of the optimization techniques in the literature might be considered metaphor-based. Such algorithms in general have attracted criticism in the research community for hiding the lack of effectiveness or novelty behind a new name or metaphor. Honestly, it is very difficult to judge which algorithm is metaphor-based and which one is not. The problem is that since separating good and bad work requires years of research and work in the area, a lot of people chooses the easiest path. Simply, based on the year of publication, anything after particle swarm optimization, genetic algorithm, differential evolution, and colony optimization is painted as metaphor inspired. It is more like racism in the real world, where since identifying good and bad people individually is hard and requires meeting people and talking to many and needs reading about ethics groups, religion, nation, and so on, the easiest thing which leads to less pain for the brain is to be racist and classify people by some crazy factor like their skin color and their religion. Because it is easy and even satisfying to classify people or anything, here algorithms, by just one or two factors, here the age of the algorithm. But the problem is that we don't have to make easy decisions that require less depth of knowledge and less thinking. We should make right decisions even by incorporating hundreds of factors if needed. Therefore, make sure to do a bit of research before using an algorithm in the literature. In this course, I'm not here to judge about the novelty of optimization algorithms, and I'll leave the decision to you and the optimization community. That is the end of this video. Thanks for watching, and I will see you in the next one.